Okay, today we're going to learn about the comparison tests. There's two. There's a direct comparison test and a limit comparison test. I highly suggest that you possibly copy these notes down first and then maybe listen to this video after you copy the notes down, as I'm going to say a few little things here and there. But it's up to you. You could always just pause as we go. Okay, so two new tests for positive term series that'll help us determine convergence or divergence of the series. And what they're going to allow us to do is we're going to compare our complicated question to a similar series that's simpler that we know how to evaluate pretty quickly. And so we'll start with the direct comparison test. So it says let 0 be less than a sub n, which is less than b sub n for all n. If the series for b sub n converges, then the series of a sub n will converge. So in other words, if the larger series converges, so does the smaller series. So in this diagram, if you look at term by term comparison here, you'll see that as x gets larger, or I'm sorry, n gets larger and larger and larger, b sub n is getting smaller. The terms are getting smaller and smaller and smaller. So when then you sum them up, the series will converge. And so if we can show that the b sub n is converging, then that will automatically assume that the a sub n is also converging, because if a sub n is smaller. This will make more sense when we do an example. And then conversely, if a sub n diverges, then b sub n diverges. So and notice up here it says a sub n is smaller than b sub n for all of these, and you can see that in the diagram for each series. So if the smaller series diverges, so will the larger. So if these terms are getting larger and larger, so when we add them up, the sum will just keep getting larger and larger. Then we can automatically assume that the b sub n series will be getting larger and larger as well. So our goal today is to find series that are either, if we think a series is converging, then we want to find something that's, we want to find a series that's larger than the given series. And if we can show that that converges, then it automatically makes our difficult problem converge. And the vice versa with the divergence. If we show that a sub n diverges, then b sub n, as long as it's bigger, will also diverge. So some good to know things. All terms must be positive. If you think a series converges, compare it to a converging series. And that series you compare it to should be larger. If you think a series diverges, compare it to a diverging series. The series you compare it to should be smaller. So the one that you're picking should be smaller if you think that divergence is going on, and it should be larger than the given series if you think it's going to converge. So some helpful hints on what to compare. You can compare, for example, n over 2 to the n to 1 over 2 to the n, because then this one's easy to show with the series we learned in 8.1 to 8.3. And then if you compare 1 over n cubed plus 1 just to 1 over n cubed, so it kind of looks like I'm just deleting the 1 here, then I can show that that series converges or diverges, and so on and so on. So the same with this one. I just dropped a power by 1. It went from n squared to n. And a lot of this is trial and error, but a lot of times you can also see what's going on. And then also 1 over the square root of n plus 3 to 1 over n. That's a good one. So we know this is a diverging harmonic series. So if we think our given series diverges, and we can show that 1 over n, which also diverges, is a smaller series, then we can prove the divergence of our original. So let's just give it a try here. So in this example, I have the series where the nth term is 1 over 5 plus 3 to the n. So I'm going to compare it to the series 1 over 3 to the n. So basically the same thing, except for I got rid of the 5. So it's a simpler series. This is a geometric series where your ratio is 1/3. That's your ratio. And that's less than 1, so this converges. So if this guy's converging, we want this to be the bigger series than the original. How do you know? Why don't you just plug in a few points or a few values into each denominator and see which fraction's bigger or smaller. So it turns out that 1 over 3 to the n is larger than 1 over 5 plus 3 to the n. Remember, the bigger your denominator gets, the smaller the overall fraction will be. So that is a larger series, and we know that this converges as we write all the terms out, so automatically this will converge. So by the direct comparison test, DCT, the series converges. The next example, let's compare it to 1 over square root of n. So like we're just ignoring the 2. That's a p series where p is 1/2, which is less than or equal to 1. And when that is the case, the series diverges. So if this series diverges, we want this one to be the smaller series. So we're going to plug a number in for n and see which denominator is bigger, which makes the overall fraction smaller. And it turns out that 1 over the square root of n is actually a bigger, that's going to be a bigger term than 1 over 2 plus square root of n. So we need to start over. So we picked a wrong series to compare it to. We need it to be smaller, and it's not. Again, you can just pick a number and plug it in real quick. So how about if we just compare it to 1 over n, which is a divergent harmonic series. I don't have to say, you can also use the p series test to prove this. So you could repeat this because it's going to be equal to 1. So we know that it diverges. And 1 over n, in this case, happens to be a smaller fraction than 1 over 2 plus square root of n when you plug in values of n. And you got to plug in more than just like 1 and 2 and 3, maybe like 10, 11, 12, something like that. Or a little smaller. But so this is a smaller series. So it's going to force, and this, we know this diverges, so it's going to force the original series to also diverge. So by the direct comparison test, the series diverges. So again, think about those good to knows. If you think a series diverges, compare it to a diverging series, and you want to show that your diverging series is actually smaller than the one you were given. If you think it converges, find a converging series to compare it to, and that series should be larger because then it would force as the terms to get smaller and smaller. When you add them up, it'll converge to some value. Okay, so going back, we got one more, and then I'm going to show you the limit comparison test. So comparing 1 over square root of n minus 1, again, just maybe taking off the -1, we're going to compare it to 1 over square root of n. That's a p series, where p is 1/2, which is less than or equal to 1. And yes, you have to show all this. So when you do the comparison test, you also have to show besides naming the series, you got to show the conditions that were met, just like you did on the last test. And we know that this converges, or I'm sorry, diverges, because p is less than or equal to 1. And this guy is smaller than the original series 1 over the square root of n minus 1. So by the direct comparison test, the series diverges. And I know in the very beginning it said a sub n and b sub n, and notice I didn't really name these terms a sub n and b sub n. Just think of it as the words. Okay, if you pick a smaller series, you're hoping it's going to diverge. That makes it the larger one diverge as well. So like I said here, and then if you think your series converges, then pick a series to compare it to that would be larger. Okay, and then next thing we can do is sometimes the direct comparison test is too messy or you can't find one, and it's just kind of creating some headaches. So often a series will resemble a p-series or geometric, just like in my two examples. Yet you can't establish a term-by-term comparison to use the direct comparison test. For some reason, it's failing. So we have another test we can use. It's called the limit comparison test. So if you have two series that are both positive, and the limit of a sub n over b sub n is some finite and positive number, then the two series will either both converge or both diverge. And I like the limit comparison test. I think it's a little easier intuitively to understand, but they both work just fine. Sometimes you can't use the limit comparison test, and you have to go back to direct comparison. Okay, so limit comparison test works well for messy algebraic series or with a p-series. For example, if I have 1 over 3n squared minus 4n plus 5, how about if I just compare it to 1 over n squared? So I'm just eliminating these terms, and I'm using that series to compare to. The 1 over the square root of 3, the quantity 3n minus 2, how about just 1 over the square root of n? And then n squared over 4n to the 5th plus n cubed. I'm just going to kind of ignore this term and look at these two guys and reduce that. N squared over n to the 5th reduces to 1 over n cubed. I don't even need the 4 there. So that would be my comparison series. Okay, so let's show you how it works. So we're going to compare this first example to just n over n squared. So basically just making my own new series with just these two leading terms here. And then I'm reducing it. I didn't even include the 4. The 4 is not going to have an impact on the answer. I got n over n squared. I cleaned that up, and that's the divergent harmonic series. And yes, like I said earlier, you can just say that. You don't have to. Everybody knows that 1 over n diverges, so it's okay to say it's a harmonic series that diverges. And what we're going to do is we're going to take the limit of our original and divide it by our comparison, the series we're going to compare it to. So I have 4n plus 1 all over n squared plus 3n minus 2. So this guy is like my a sub n, and I'm dividing it by my b sub n if this is b sub n. So you're going to take the reciprocal of 1 over n and multiply it by your numerator, and that's always going to happen. So try just to go straight to this step so you can save yourself some writing, and just go ahead and flip that denominator term. And we're approaching limit as n goes to infinity. And so when I do my math and I clean all this up algebraically, I end up with 4n squared plus n all over n squared plus 3n minus 2. And we can do top heavy, bottom heavy, equal powers with polynomials. And so this ratio becomes 4 as n gets super large, which is finite and positive. That number is a finite number and it's positive. If it were infinity, that wouldn't be the case. It has to be a positive number here. And so we say by the limit comparison test, LCT, the given series diverges. Okay, so it's by the limit comparison test, your answer is going to follow what you compare it to. We compared it to a divergent series. So if we get a finite and positive limit at infinity, then our given series diverges. And again, and conversely, if this converged, this would converge as long as we got a finite and positive number. Okay, so how about the square root of n over n squared plus 1? I'm going to just kind of take these two terms and make my own series and reduce n to the 1/2 over n squared to 1 over 3n squared. That's a p series. P is greater than 1, it converges. So we're going to do the limit comparison test of the original divided by the one we're comparing it to. And when you divide by a fraction, you're really multiplying by its reciprocal. So I'm skipping this algebraic step there. Then I combine these n's by adding their exponents. And then I take the limit at infinity, which is going to be 1, finite and positive. So by the limit comparison test, the given series converges. So I would be, if this were a test question, I'd be looking what series you compared it to. You would have to state the series and the condition that's met, and then determine if that converges or diverges. And then you show step 2, where you do the limit of the ratio of the two series. And then your last step would be by the limit comparison test, the given series converges. Oh, and it's good to say finite and positive, by the way, because that's just following the instructions or the test. Okay, last two. I'm going to compare n times 2 to the n over 4n cubed plus 1. How about, in this, again, trial and error, but how about if we just work on the terms that get really, actually, if you look at this whole part right here, this n and n cubed can be reduced to n squared. So I took off the 4, basically, and took off the 1. And that's my series I'm going to compare to. And this one is a little tricky. I'm going to use the nth term test. I want to see if it diverges. So that's when you take the limit, and as long as you don't get 0, it diverges. So, and this is a divergence test. This is only for divergence. So as long as I don't get 0, I know it diverges, and I'm good to go. So when you plug in infinity, you get infinity over infinity. So I have to use L'Hopital's rule. So I'm taking the derivative of the top and the derivative of the bottom. I still get infinity over infinity. So I'm going to do L'Hopital's rule again. So we're going to L'Hopital's again. And when we do that, we just get the number 2 in the denominator. And that ends up being infinity over 2, which is infinity, which diverges. And so then we're going to take the ratios of our, given series and our the one we found, and I'm going to flip this guy. That's right here. I'm going to multiply it by the original nth term, clean up the algebra. I got a number that's finite and positive, so you want to state that. So by the limit comparison test, the series diverges. So it just follows. If this guy diverges and we can show this is finite and positive, then this diverges. Or converges, works as well. All right, last one. So if you look at this guy, this has an exponent of 1, and this n plus 1, the n has an exponent of 1. So I'm not really concerned about that so much as how about just 1 over 2 to the n minus 1, and maybe even make it simpler. And this is like just trial and error, but it is a helpful hint on the front, just to kind of the simplest version of all this, which is just 2 to the n in the denominator. So if I go ahead and look at this as a 1/2 ratio, it's a geometric series. The ratio's 1/2, which is less than 1, so we know the series converges. So I do the limit of the ratio of the two series, so n over n plus 1 times 2 to the n minus 1 in the denominator, divided by the reciprocal of 1 over 2 to the n. And then I get clever with my algebra. I distribute the base 2 to the n and 2 to the negative 1 and write it this way. So I broke up the exponents. Canceled my 2 to the n's right here. And then I did a little cleanup. This is n over n plus 1 times 2 to the negative 1. I think I brought this up in front. So the exponent would be positive, which is 2n over the n plus 1. And then we know that is 2 when we take that limit, finite and positive, so the given series converges. And that's all there is to it. It's just a little bit more work and effort to find out if the series converges or diverges.